In this unit, we're going to explore the idea of entropy. In this module, we are going to explore the idea of entropy and learn how to qualitatively assess systems to determine whether they are spontaneous or not based on an increase in the entropy or an increase in the disorder of the system. So as we mentioned before, entropy is about disorder or the number of ways to arrange something. Specifically, it is a thermodynamic function that represents the number of ways to arrange system components in energetically equivalent states. So the more ways I can arrange something, the more disorder there is, the higher the entropy. When you first learned about entropy, you may have used this as an excuse to not have to clean your room, that you were fighting nature by cleaning your room and decreasing the disorder or randomness. A better way to look at entropy is as a dispersal of energy. If we take a solid and a liquid and combine them and we get a solution, we have dispersed the energy of the solid and liquid so that it is more random and there are more ways to arrange that energy. Therefore, we have an increase in the entropy going from reactants to products. The same thing can be said for mixing two liquids. As they mix, there are more ways to arrange those molecules, there's more dispersal of energy, and therefore an increase in the entropy. As we talked about for enthalpy or volume or temperature, entropy is also a state function. It depends only on the initial and final states and does not matter how we get from initial to final. Therefore, delta S equals entropy final minus entropy initial. When delta S is positive, we see an increase in the entropy of the system. When delta S is negative, we see a decrease in the entropy or a decrease in the disorder or a decrease in the dispersal of energy. Let's look at how heat flow, entropy, and the second law are related. When we place ice in water and hot water, heat flows from the water into the ice. According to the second law, this happens because we're dispersing heat. We're taking the energy that's in the hot water and spreading it out more. As a result, we also see the ice melting, but more importantly, the entropy of the universe is increasing. Therefore, this is a spontaneous process. This is why when we put ice in a drink, we suddenly don't have more ice cubes forming. Some examples where we see positive delta S values or increases in entropy are some phase changes, for example, going from solid to liquid to gas, reactions where we have more moles of gas on the right side or on the product side than on the reactant side, solids dissociating into ions when dissolved, such as in water and forming an aqueous solution of a salt, or an increase in molecular complexity. If we take two atoms and form a molecule, we're increasing the molecular complexity and therefore we're increasing the delta S or increasing the entropy. Note that when we talk about the entropy here, we're looking at the entropy of the system, not looking at the entropy of the surroundings or of the universe. For phase changes, we have a positive delta S when we go from solid to liquid to gas. We have more ways to arrange the energy when we go from the solid to the liquid to the gas than in reverse. So for negative delta S, we see gas to liquid to solid because we're reducing the ways that we can disperse the energy. We're decreasing the disorder in the reaction. So we have a negative entropy value or a decreasing entropy value. Let's look at an example. Of the following, which system shows a decrease in the entropy of the system? In this case, we're looking for a decrease in entropy. So we're looking for a decrease in the disorder, or a decrease in the number of ways to disperse the energy. When I look at option A, what I actually see is an increase in the entropy because I'm going from the liquid phase of a substance to its gas phase. There's more ways to disperse the energy, more disorder in that system. When I look at option B, I've got sodium chloride in the solid phase going to aqueous ions. This is also an increase in the entropy because I'm dispersing those ions throughout that solvent. When I look at option C, I have 2 moles of gas on the left and 2 moles of gas on the right, but I'm increasing the molecular complexity because I'm going from elements to a molecule, so I will also see an increase in the entropy. On option D, I see 2 moles of gas on the left and only 1 mole of gas on the right. Therefore, I'm going to see a decrease in the entropy of this system. Well, we talked about entropy of the system. Now we need to worry about entropy of the universe.